The most critical machine learning interview question asks you to do more than define a term. It asks you to design an end-to-end ML system. High-level technical interviews verify that a candidate can integrate dozens of isolated concepts into a single functional production pipeline. This pipeline begins with a clear taxonomy. Artificial intelligence builds machines simulating human intelligence. Machine learning is a subset enabling computers to learn patterns without explicit programming. Deep learning uses multi-layered neural networks to extract higher-level features. Two primary paradigms dictate how this data is processed. Supervised learning maps known inputs to labeled outputs, while unsupervised learning identifies hidden structures and patterns in unlabeled data. Selecting the correct paradigm, supervised or unsupervised, determines the fundamental requirements of the pipeline before the first piece of data is even ingested. The first node of the pipeline is data strategy. Raw data cleanly fractures into two parts: a large training set used to teach the algorithm, and a hidden test set used to evaluate its final performance. Cross-validation, specifically the k-folds method, ensures the model generalizes to new data. By partitioning the data into multiple subsets and rotating which part is used for testing, we prevent the model from merely memorizing a specific sample. Feature engineering follows, where we manually transform raw inputs into variables that expose the underlying patterns of the dataset to our algorithms. Every decision made during this engineering phase is governed by the bias-variance trade-off. Bias represents error introduced by overly simplistic assumptions, often leading to underfitting. Conversely, variance represents error from extreme sensitivity to training noise, causing a model to overfit and capture random fluctuations as valid patterns. Every subsequent algorithm, regularization technique, and evaluation metric is a specific tool designed to master the tension between these two sources of error. We move to the model selection node, matching our chosen algorithm to the specific structure of the data. For predicting continuous numerical values, we use linear regression, assuming a straight-line relationship. For categorical outputs, logistic regression squashes values through a sigmoid function to produce a probability between 0 and 1 for binary classification. Support vector machines classify data by finding an optimal hyperplane that maximizes the margin between different classes. Alternatively, naive Bayes classifiers use Bayes' theorem, assuming every input feature is entirely independent of the others. When the data is unlabeled, we introduce unsupervised learning via the k-means algorithm. It organizes data by iteratively calculating the distance between points and a predefined number of central nodes, called centroids. Choosing these algorithms depends on whether data is continuous, categorical, or unlabeled, as each introduces a different level of baseline bias into the system. Decision trees provide a highly interpretable model, using recursive splitting to partition data based on the features that provide the most information gain. However, a solitary decision tree is prone to high variance. Without constraints, the tree will grow until it has perfectly memorized the noise of the training set. Ensemble methods solve this by combining decisions from several base models to achieve a stable result.
Bagging, like the random forest algorithm, builds dozens of independent decision trees in parallel using different data subsets. By aggregating these parallel predictions through majority voting, bagging reduces the variance of the final output without increasing its bias. Contrast this with boosting. It trains trees in a sequential order, where each new tree focuses specifically on correcting the errors and misclassifications of the tree that preceded it. Ensembles serve as architectural corrections, used to lower variance or bias when a single algorithm lacks the mathematical complexity to generalize effectively. The pipeline enters the optimization loop, the stage where the model actively adjusts its internal parameters to minimize its errors. Gradient descent is the primary tool for this task. It is an iterative optimization algorithm that updates parameters by finding the local minimum. To prevent this optimization from leading to overfitting, we apply regularization. These techniques add a penalty term to the loss function to discourage the model from fitting the training data too closely. L1 regularization adds a penalty equal to the absolute value of the coefficients. This drives less important feature weights to 0, creating a sparse model. L2 regularization adds a penalty equal to the square of the coefficients. This shrinks all weights smoothly, distributing error across the entire feature set. In deep learning, neural networks pass data through hidden layers of weighted nodes to reach a prediction and calculate an error. Backpropagation then proceeds backward through the network, updating those weights by calculating the gradient of the error function. For deeper networks, we employ dropout. This randomly deactivates specific neurons during training, preventing them from co-adapting and forcing the network to learn more robust features. Optimization updates the model based on its errors, while regularization constrains that update process to prevent the network from memorizing noise. We reach the final node, evaluation. Relying solely on accuracy is misleading, particularly in cases with imbalanced datasets, where a model can be highly accurate while failing entirely on the minority class. Proper evaluation requires a confusion matrix. This grid categorizes predictions as true positive, true negative, or false negative. Precision is the ratio of true positives to total positive predictions, measuring reliability. Recall is the ratio of true positives to actual positive instances, retrieving every relevant case. The F1 score combines these two metrics. By calculating the harmonic mean of precision and recall, it provides a single, robust measure of the model's performance on imbalanced data. Finally, the ROC-AUC curve graphically illustrates the trade-off between the true positive rate and the false positive rate across different classification thresholds. Evaluation is the final check on our architectural choices. Without these matrices, an optimized model might provide high confidence for entirely incorrect predictions. Zooming out reveals the complete system. We have engineered raw data, balanced the bias-variance trade-off through algorithm selection, optimized via gradients and penalties, and validated performance through precision matrices. Approaching the technical interview as an architectural challenge proves you possess the mindset to build a unified, production-ready intelligence engine.